Hello, student. This week is seventh week of this 2021 course. Okay, in this week, we'll deal with Diffie-Hellman Key Exchanges. Okay, actually, Diffie-Hellman Key Exchange, this system is first published for public key algorithm. Nowadays, a number of commercial products employ this key exchange technique. Purpose of this algorithm is to enable two hosts to exchange or share a secret key securely, which can be used for subsequent encryption of messages. However, the algorithm itself is only refer how to exchange over the keys. This Diffie-Hellman Key Exchange uses a discrete logarithm for computing. Okay, let's check the basic of discrete logarithm. In Diffie-Hellman crypto system, the system uses a large prime number q. It's integer, large integer number. Also, must use integer number alpha. That is the primitive root of prime number q. Then, what is a primitive root? It is said that alpha is a primitive root of q if alpha mod q, alpha square mod q, alpha q minus 1 power of q minus 1 mod q generate all the integers within the range from 1 to q minus 1. The order is not important. It only needs to have all the integers within this range. Okay. The q prime number has something to do with the size of key space. The size of q determines the size of key space. In cryptography, the larger key space, the better. Why? larger the key space, the harder it is gets to the valid key. Anyway, component with harder to crack the crypto system with the brute force attack. Okay. So the prime number Q can be as large as possible. Okay. Let's see the example of prime number 19. If alpha is 8, alpha square mod Q result in 7. Alpha power of 3 mod 19 result in 18. Alpha power 4 mod 19 result in 11. Alpha 15, 12. Alpha 6 power 6 mod 19 result in 1. But this one does not show all the integers between 1 and 18. Some integers are missing. For example, there is no 3, no 4, no 5, no 6. So the number 8 is not primitive root of prime number 19. However, let's check this one, alpha 15. Alpha mod 19, 15, result in 15. Alpha mod power 11 mod 19, result in 3. Alpha power 11, 18 mod 19, result in 1. So this one contains all the integers between 1 and 18. So number 15 is a primitive root of the prime number 19. Okay. So anyway, to protect from the enemy's cracking Diffie-Hellman cryptography system. So prime number Q the number q must be prime number. Okay, both sides, each side, user A, user B, want to share a secret key via online. Each already know the Q and alpha. Q is prime number. Alpha is the primitive root of prime number Q. Okay, user A first select random integer XA. And compute. This is called blind key because this is function of XA based on alpha and Q. Okay. So A calculate YA. And send YA to B instead of XA. XA must be secure. A keeps the XA securely. Similarly, B select random XB and compute YB, blind number YB. YB is generated from the function of XB based on alpha and Q, same alpha and Q. And send this blind key to user A. Now check. This is A side. User A calculate K. When user A receive YB from B, YB power of XA mod Q generate K. Yeah, YB is A side. This equation means this one. This equation same as this one. We can change order like this way. Okay, change order this one. And this means same as this one. Okay. This one equation is this equation. User B calculate the shared key K. When it receives YA from user A. Then we can see this equations result in the same result. Then the A and B share the same secret key K. Okay. Here, let's see this equation example. Okay. This example. This equation can compute this equation. Okay. We can this result, this result, okay, this result, okay, can be 10. Okay, let's summarize the Diffie-Hellman Key Exchange algorithm. Q alpha. Both sides must have a Q alpha. That's the reason why we call this Q alpha as global public element. Q must be prime number. Alpha is primitive root of Q, less than Q. A side, select private XA, XA less than Q, calculate YA as function of XA based on alpha and Q. B side, select private value XB less than Q, calculate YB using the function of this equation, and user A side can generate K like this, user B can generate like this. Okay, let's see the example again. Alice and Bob wish to share a secret key. They agree on prime number Q 353 and the prime root of Q alpha 3. Then A select private value XA 97, B select private value XB 233. Each compute its public key, YA, result in 40, YB, then for A. Then they compute the session key. Okay. A side, Alice, okay, using the public key of Bob, compute key like this, result in 160. Bob, using the blind key of Alice, and compute like this, result in they are same. Then Alice and Bob can share the same key of 160. However, the original Diffie-Hellman Key Exchange method has a weak point in authentication, they are weak in the man-in-middle attack. Okay, here, attacker is thus. Alice and Bob wish to share a secret key. Thus, interfere between Alice and Bob and attack this system. Okay, same is Alice generate the secret value XA and the public key YA like this. Bob also private value XB and generate the YB like this one. And Alice send the YA to DARS. That's intercept this YA. Before reaching Bob. And thus generate two private values XD1, XD2. XD1 is for Alice, XD2 is for Bob. And they generate YD1 based on XD1, YD2 based on XD2. Because here Alice does Bob already know the global parameter alpha and Q. Okay. Sorry, this is long. The XD2 is Alice, not this one. XD1 is Bob. Then return YD2. And thus send YD1 to Bob instead of YA from Alice. Then Bob send YB to Alice, but does intercept this one and calculate the secret key. This one, XD1, this one. So does also, Bob also calculate the secret key, this one. Bob does share K1. Does also calculate this key. Alice calculate this key. Alice and does share K2. Problem is Alice considers this K2 as the key between Alice and Bob. Also, Bob and Das, Bob also consider this key, K1, as the secret key between Bob and Alice. But Das attacking this system. Okay, currently the commercial products solve this authentication issue to protect man in the middle attack. Okay.